Today we're going to cover shear force and bending moment diagrams. This is material that you might have seen when you took statics, or you definitely saw when you took mechanics and materials, and it's something that we just can't escape. Forces and moments that apply to bodies, or how we determine the stresses and strains that are transmitted through them. So let's start. Let's imagine that we have ourselves a beam. It's supported at A and B, and we have a series of forces and moments and distributed loads that are applied to that beam. If we were to take the beam and section it down its middle, we would expose internal normal forces, shear forces, and bending moments that are applied to that beam. If we were to take a series of sections, not just one, but many sections across this beam, we would find that the internal normal forces, shear forces, and bending moments change as we move along the geometry. And in order to determine how they change, when they become maximum or minimum, we need to create what are called shear and bending moment diagrams, right? Diagrams that tell us how those forces and moments evolve along the geometry. So the question is, how do we create these diagrams? Well, the first thing we need to do is we need to know the sign convention. What's a positive force or negative force? What's a positive moment or a negative moment? Then we need to know how to apply calculus or singularity functions in order to solve for how those forces and moments evolve as a function of distance. So we're going to find equations for those values. And then finally, we need to plot the answer. We need to plot the values as a function of position, right? So let's start with sign conventions. The sign conventions for these forces and moments. Normal force. Normal force is the force that is transmitted along the beam's cross section, right? So perpendicular to its cross-sectional area. Positive normal force is one that causes tension or a stretching mode within your geometry. So if you were to section your body, if there is a force that is exposed that's going to make it stretch on each side of the section, then that is positive normal force. While if we were to section our body and there's a force that's going to make it squish or compress down, then those are negative or compressive normal forces. Shear force. Shear force is a force that's transmitted across our cross-sectional area of our beam. A positive shear force is one that is going to make us step up, over, and then return back down. So if we are to section our body, if there is a shear force that is applied, say at a support, and then we have a force that we hit before we section, then that's a positive sense of a shear force. While on the opposite end, if we have a force that initially starts downwards and then goes across, then we have a negative shear force applied to our body. We start at zero, we step down, then we return to zero at the end of the section, right? Now, bending moments. Bending moments cause bending in our beam, cause a kind of change in shape of our beam. We'll find that positive bending moments cause a concave upward bend of our geometry. So our geometry wants to bend upwards, while negative bending moments cause a concave downward bending of our geometry, right? So it's going to bend downwards. So when we think about these moments and where they're applied, we've got to think, okay, if I were to section this beam and I only had one side, the left or the right hand side, what shape will the beam take? Bend upwards or will it bend downwards? Similarly here, we had to take a section. What shape would the subsequent section take on, right? So now we've got our sign conventions down. Let's then go into how do we actually solve for our equations. And we'll start with the calculus approach, which is my favorite. I love the calculus approach. For me, it helps me. It's easy to understand. Let's step through it. Let's start with, say that we encounter a concentrated shear force, right? So we have a beam. It's supported at A and at C by simple supports. And in the middle, we have applied a concentrated shear force, VB. That concentrated force is going to create a step change in our shear force diagram, where the change in shear force, delta V, is equal to the integral from VA to VB over dV. And that is basically equal to VB minus VA, right? So the step change from A to B is what we are after here. If we were to solve that, we'd end up finding that we start at 0, we step increase by the value of VA, which is our support, and we are constant, our shear force is constant until we encounter B. We encounter that applied shear force that is negative. It's going to step us all the way down, and then it will be constant until we get to C, at which we return to 0. So notice in the shear force diagram, we start at 0, we have a step increase by VA. When we move through B, we decrease by VB, and then when we get to C, we step back up to 0, right? So now let's do another one. Let's look at what happens when we encounter a coupled moment that's applied to our geometry. So say we have a beam, we have an applied coupled moment at the middle of it, MB, and then we have some simple supports, MA and MC for this geometry. The coupled moment is going to give us a step change in our moment diagram, where the delta M, the change in the moment, is equal to the integral from A to B of the moment, which is equal to MB minus MA. So our moment diagram, how does that look? Well, we'll start at our support of MA, concave upward. If we were to do a section line, MA is going to bend the beam up. So we're going to step change by MA. And then there's nothing happening until we get to B, at which we have a step change, concave downwards, and B is going to make our beam want to bend concave downwards. So we have a step change by the value of MB. And then nothing happens until we encounter C, where we have another moment, coupled moment, concave upwards, MC. So here again, we start at 0 and we end at 0. And each of these coupled moments that are applied or that are supports give us a step change in our moment diagram. Let's actually correct this. This is a moment diagram here, right? So now we've got the two simplest down. We have a shear force applied, or we have a coupled moment that's applied to our diagrams. Now let's get a little bit more complicated. What happens when we have a distributed load, right? So forces, they can be concentrated at one point, but in real geometries, most often force is distributed over a cross-sectional area. Force is actually distributed over a surface, not just at one contact point. With those type of forces, we call them distributed loads, and they have units of force over distance or over length. The easiest one, distributed load we can deal with, is when that distributed load is constant, meaning that the force is a constant value distributed over the length. So say force is 10 newtons per meter, right? So you have a constant force that's applied across the length of your geometry. A more complicated distributed load is one that is a linear function, where the force has a slope, it's a linear function, that either decreases, in the case here, or increases over the length of your geometry, right? So a linear function is like a y is equal to mx plus b, a simple equation, right? The most realistic distributed load, but also the hardest to deal with, is when the distributed load is a nonlinear function, meaning it's like a exponent or a polynomial or some crazy equation. That's where the distributed load can just kind of change dynamically over the length, and it's usually in a form of an equation. This is a little bit more difficult to handle, but we have ways of dealing with these distributed loads, and it's all through calculus, right? So let's start with a basic example, and let's use calculus not only to solve a distributed load problem, but to find the equations for the shear force diagram and the bending moment diagram for basically any problem. So let's start with an example here. We have a simply supported beam. It's embedded in a wall, and there is a distributed load, W, that's applied to it. That is a constant distributed load. It has some reactions at the supports of a reaction force, RA, and a couple moment, MA, which are we replace the wall with the reactions, right? So let's start with the first equation, which is a relationship between our distributed load, W, and the slope of the shear force diagram, where the slope of the shear force diagram, dV dx, so the change in shear force over a change in distance, is equal to Q, where Q is equal to the negative value of our distributed load, right? So if we know our distributed load, we know W, we can solve for the slope of the shear force diagram. We know what slope it takes. And that slope is basically negative W. That's the slope. Now, if we were to take this equation, move dx to the right-hand side, and integrate indefinitely both sides of the equation, we'll end up with a calculus equation for the shear force, where the shear force, Vx, is equal to the indefinite integral of Q dx plus C, where C is a constant of integration, right? So then if we take our example here where we have W, and we go ahead and do that integration, negative W in there from 0 to L, which is the length of the beam, and then we have a constant of integration, we can solve for the equation for the shear force diagram, where the shear force diagram, Vx, is equal to negative W times X plus RA, which is our force of the support. And how do we find the C is RA? Well, if we set V equal to V at position 0, V at position 0 is equal to RA because we have that reaction. That is our constant of integration, right? So now just doing some simple calculus, we basically solved for the shear force diagram. We found the equation that defines this diagram, and we can draw it, right? Now that's all fine and dandy, okay. But what about the bending moment? We've got to find that, right? So let's consider that the slope of our bending moment diagram, dm dx, or the change in the bending moment over a change in distance, is equal to the shear force, right? So the slope of our bending moment diagram is equal to the shear force at any particular position. So if our shear force is changing, then our slope is changing in the bending moment diagram. It's kind of crazy, right? Well, if we move dx to the right-hand side, and we integrate both sides of this equation, we can solve for the bending moment equation. We can actually solve for the equation that defines the bending moment diagram, where the bending moment, M, at any position of x, is equal to the integral of the shear force, dx, plus a constant of integration, C. So now let's go and look at our example. If we were to do that integration over our given beam from 0 to L, we can go ahead and plug in our Vx equation that we've already found, and then we can integrate from 0 to L, and we'll find the following, that our moment is equal to negative W times x squared divided by 2 plus RA times x plus our constant of integration, right? Now to solve for that constant of integration C, let's set M equal to 0. What happens when M is at, where x is at 0, at the beginning of our beam? Well, at the beginning of our beam, the only thing that should be applied is our reaction MA, right? The reaction that we have in our body, which is a negative MA, concave downwards. So if we put that, if we know that C is equal to negative MA, now we have an equation that defines our bending moment diagram. Then all we've got to do is go ahead and plot that equation. We're at 0, we're at MA, and then we have this polynomial that falls to 0 at the end of the beam, right? Pretty good, pretty good. And so finally, something that we might need to do can often happen when we have a complex beam is sometimes our bending moment is not maximum at the beginning or the end of our beam, but somewhere along its length. And we want to know where the bending moment is maximized because that's where our stresses could be maximum in a beam. So to find the maximum bending moment, all we've got to do is note that the bending moment is maximum where the slope of our moment diagram is equal to 0, meaning that we're transitioning from a max value and then we are going to decrease in our bending moment. So that means the slope, dm dx, is equal to 0, but it also means that the shear force is equal to 0. So if we were to take the shear force equation that we have, set it equal to 0, and solve for the position x, that'll tell us where the bending moment is maximized. And then we can simply take that x, plug it into our moment equation, and know the value or values for maximum bending moment, right? So the calculus approach to me is fairly straightforward. Just doing a little bit of calculus, a little bit of integration, we can find these equations. However, there is another approach we can use to solve for the shear force and the bending moment diagrams. And that approach is singularity functions. In our book, we can find the table for singularity functions in table 3-1. And in singularity functions, we use angular brackets, which help us to basically find the equations for shear force and bending moment by stacking these angular brackets together for different applied forces and moments. So let's kind of walk through these. Let's note that the brackets that we use, that is kind of the heart of this. But the power that we put on the brackets depends on the type of loading that is applied. So for example, if we have a concentrated moment, then we'll put the value of that moment outside of the brackets. And then for concentrated moments, we're going to have brackets from x minus a, where a is the position along the beam where that moment is applied. And then our power is going to be -2 for a concentrated moment. We use a power of -2. For a concentrated force, so an applied force to our body, we'll put the value of that force, say it's VA, and we'll put brackets x minus a, where a is a position where that concentrated force is applied, and then our power for concentrated forces is -1, right? For, say, a unit step of applied load, so say for a distributed load of a constant value, W, we'll put W on the outside of the brackets, and then to a power of 0, which tells us that that is a load that is continuously applied. Once we reach position A, that force is applied continuously along the beam. If we want to deactivate it, so say we have a concentrated force that's applied over from A to a certain distance, B, then we'll need to put negative W x minus B to 0 so that we can so that's activated from A, and then we turn it off once we get to B. Very important thing to note. And then finally, say we have a ramp. So say we have a distributed load that's not constant, but it's a function. In that case, W is a function in brackets to a power of 1 will give us that activation. So generally what we would do is if we're given some example with different coupled moments, applied loads, and distributed loads, we create a long form equation adding all of these terms together. And then we would integrate these terms. So once we have that full equation together, we would integrate using this form. So it gives you the form of integration in order to solve for the shear force equation, and then also to solve for the bending moment equation. So in essence, these singularity functions basically allow you to build like Legos your basic equation for the shear force diagram and the bending moment diagram. Now, it may seem a little bit complicated, but we'll do some examples in class in order to see kind of how this works between the calculus approach and the singularity functions. So with that said, once we know the sign conventions for forces and moments, and once we apply either the calculus approach or the singularity function approach, we can easily draw our shear force and bending moment diagrams. And in these diagrams, the values where shear force is maximum or bending moment is maximum tend to be the critical locations where we can expect stresses to be high in our geometry and where we might expect failure.